October 12, 1898. Bethlehem Steel Works, Pennsylvania. The morning shift begins with a sound every machinist dreads, the sharp crack of hardened tool steel fracturing against the workpiece, followed by the grinding screech of metal destroying metal. Samuel Morrison, plant foreman, watches his best lathe operator step back from the machine as cherry-red heat spreads across the cutting tool's edge. 22 minutes into the shift, production stops again. Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old machines' legacies alive. Replace the tool, Morrison orders, checking his pocket watch for the third time that hour. The mathematics were brutally simple. Each cutting tool cost 0.47 and lasted an average of 22 minutes when machining hardened steel components. 8 tools per shift per machine. 73 machines running across 3 buildings. The numbers told a story of American manufacturing held hostage by metallurgical limitations that European steelmakers had solved decades earlier, then weaponized into commercial dominance. The problem wasn't the machinists or the machines. American lathes matched British precision. American workers trained just as rigorously. The failure lived in the cutting tools themselves, in the fundamental chemistry of carbon tool steel that had remained unchanged since the 1840s. Carbon steel achieved hardness through heat treatment, heating to 1400 degrees Fahrenheit, then quenching in water to lock the crystalline structure into rigid hardness. But that hardness disappeared the moment friction heat from cutting operations raised the tool's temperature above 400 degrees. Machining hardened steel components generated temperatures exceeding 800 degrees at the cutting edge. The tool softened, deformed, and failed with mechanical inevitability. British metallurgist Robert Mouchet had solved this problem in 1868 with his revolutionary tungsten steel alloy. Self-hardening steel, he called it, though the real innovation was heat resistance. Mouchet's steel retained hardness at temperatures approaching 600 degrees, allowing cutting speeds that carbon steel could never match. British machine shops operated at production rates American manufacturers could only envy, while American factories paid $2.40 per pound for imported Mouchet steel versus 0.18 per pound for domestic carbon steel, and waited 6 months for deliveries that British suppliers controlled absolutely. Morrison studied the production reports with growing frustration. Bethlehem Steel's new naval armor contract required machining hardened steel plate to tolerances measured in thousandths of inches. The contract specified 2,400 armor panels delivered within 18 months. At current production rates, limited entirely by tool steel performance, they would miss the deadline by 7 months and forfeit $340,000 in penalty payments. British shipyards faced no such constraints. Their Mouchet steel tools cut continuously for hours, while American tools failed every 20 minutes. The strategic implications extended far beyond one steel mill's production troubles. American industrial ambition demanded manufacturing capacity that European metallurgy refused to enable. Railroad expansion required mass production of hardened axles, wheels, and coupling mechanisms. The emerging automobile industry needed high-speed machining to make vehicles affordable beyond wealthy customers. Naval rearmament programs specified armor plate and gun barrel production at scales that carbon tool steel made economically impossible. European metallurgists defended their monopoly with mathematical certainty and century-long tradition. Dr. Heinrich Werner, consulting for multiple American manufacturing firms, explained the technical barriers with academic precision during his quarterly inspection visit. Carbon provides hardness, he noted, gesturing toward Morrison's failed cutting tools. But carbon also creates thermal sensitivity. The higher the carbon content, the greater the hardness when cool, but also the greater the softening effect when heated. This is fundamental materials science. The chemistry permits no alternative. American attempts to circumvent British tool steel monopoly had failed systematically. Pittsburgh steelmakers added manganese for toughness. Cleveland foundries experimented with silicon for hardness. Detroit metallurgists tried nickel for thermal stability. Every approach produced steel that either failed to achieve adequate hardness or lost that hardness even faster than carbon steel when heated by cutting operations. The chemistry seemed to permit no escape from the fundamental trade-off between hardness and heat resistance. But 300 yards from Morrison's production floor, in a cluttered corner of Bethlehem Steel's experimental foundry, two men were testing alloy combinations that European metallurgists had dismissed as metallurgically pointless. Frederick Winslow Taylor, 42-year-old efficiency expert and self-taught metals researcher, stood beside Monsell White, 34-year-old chemist with unconventional ideas about heat treatment temperatures. Their experimental furnace glowed orange in the dim foundry light as they prepared another test batch of tool steel containing tungsten and chromium in proportions that violated every principle Werner had explained. Taylor made careful notes in his leather-bound journal. Test number 4847. Composition 18% tungsten, 4% chromium, 0.67% carbon. Heat treatment temperature 2,200 degrees Fahrenheit. The numbers seemed absurd. Conventional wisdom insisted that heating steel beyond 1,600 degrees burned the metal, destroying its crystalline structure and rendering it useless. But conventional wisdom had produced tools that failed every 22 minutes while British competitors operated at speeds American manufacturers could never match. Sometimes, progress required testing what metallurgical tradition insisted was impossible. Frederick Winslow Taylor had apprenticed in machine shops for 26 years, studying metal cutting with the methodical intensity that had carried him through night school while working 12-hour factory shifts. No formal university training, no European metallurgical credentials, just systematic observation of what worked and relentless documentation of what failed. Monsell White brought chemical precision to Taylor's practical obsession, a trained chemist willing to question assumptions that European metallurgists treated as immutable law. Their partnership began with a simple heretical question. If Robert Mouchet's tungsten steel retained hardness at 600 degrees by adding tungsten to carbon steel, what would happen if they added chromium as well and pushed the heat treatment temperature far beyond the conventional limits that European tradition respected? The established metallurgists at Sheffield and Essen insisted chromium made steel brittle. Taylor and White decided to test whether that brittleness might disappear at the extreme temperatures that conventional wisdom called burning. The experimental program consumed 18 months and 40,000 individual cutting tests. Each test required precise alloy preparation, carefully controlled heat treatment, then actual machining operations measured for cutting speed, tool life, and dimensional accuracy. White held chromium content constant at 4%, while Taylor varied tungsten from 2% to 20% in half% increments. The early results validated European skepticism with mechanical brutality. Test 1047 at 2% tungsten and 4% chromium failed at 450 degrees, no better than carbon steel. Test 2104 at 4% tungsten shattered under cutting loads, the chromium brittleness proving exactly as destructive as German metallurgists predicted. Test 2091 at 6% tungsten showed promise, maintaining hardness to 520 degrees, but the performance varied wildly between batches. Some samples cut beautifully, others failed within minutes. The inconsistency made commercial production impossible. Taylor suspected the variable was heat treatment temperature, not alloy composition. European practice specified heating to 1,400 degrees for hardening, a temperature metallurgists had established through century-long tradition. But Mouchet's original patents mentioned heating to 1,600 degrees, 50% higher than standard carbon steel treatment. Taylor proposed pushing far beyond even Mouchet's specifications into temperature ranges that metallurgical textbooks explicitly warned against as destructive to steel's crystalline structure. White modified their experimental furnace to reach 2,400 degrees, installing specialized fire brick and forced air systems that consumed coal at alarming rates. Bethlehem Steel management reviewed the experimental budget with increasing concern. $47,000 spent over 18 months with no commercial product to show for the investment. The amount equaled $1.6 million in contemporary terms, an enormous sum for research that European experts insisted was chasing metallurgical impossibilities. The breakthrough emerged at test number 4047 in January 1900. 18% tungsten, 4% chromium, 1% vanadium, 0.67% carbon. Heat treatment at 2200 degrees Fahrenheit for precisely 47 minutes, then oil quench to 150 degrees, followed by tempering at 1100 degrees for 2 hours. The resulting tool steel retained full hardness at temperatures exceeding 1000 degrees Fahrenheit, hot enough to glow cherry red under machine. Shop lighting. The cutting tests produced results that seemed to violate physical law. Taylor's new steel-cut hardened workpieces at 40 feet per minute compared to 10 feet per minute for the finest Mouchet steel. Tool life extended to 4 continuous hours of cutting versus 22 minutes for conventional tools. Most remarkably, the steel actually grew harder as it heated during cutting operations, a property that European metallurgists would later identify as secondary hardening, but which Taylor and White discovered purely through systematic empirical testing. Bethlehem Steel's management demanded proof beyond laboratory conditions. The Paris World Exhibition in May 1900 provided the perfect stage for public demonstration. Taylor arranged for a precision lathe to be shipped to the exhibition hall along with samples of hardened steel workpieces and a selection of cutting tools made from both Mouchet steel and his new high-speed formulation. The demonstration began conservatively, with Mouchet steel cutting at standard speeds. The British tool performed exactly as expected, producing smooth chips and maintaining dimensional accuracy while the cutting edge remained cool enough to touch bare-handed. Then Taylor switched to his tungsten chromium steel and increased the cutting speed to 40 feet per minute. Within 30 seconds, the tool edge glowed visible red. The crowd pressed closer, expecting catastrophic failure. The tool continued cutting smoothly as metal chips sprayed blue-hot from the glowing edge. Taylor let the demonstration run for 20 minutes, the tool glowing brighter as cutting speeds increased, yet the dimensional accuracy remained perfect, and the tool showed no signs of wear or deformation. European metallurgists in attendance demanded to inspect the equipment for hidden cooling systems or substituted tools. They found nothing but a cutting tool operating at temperatures that should have rendered it useless, yet performing better than any tool steel previously manufactured. Dr. Adolf Martens, director of the Royal Prussian Materials Testing Office, declared the demonstration a laboratory curiosity unsuitable for factory production. British representatives from Mouchet Steel Company threatened patent litigation, claiming Taylor had merely modified their existing formulas. German machine tool manufacturers insisted the extreme heat would damage equipment and endanger workers. But American factory owners saw something European academics missed. They saw cutting speeds that could transform manufacturing economics and production capacity that could finally break European metallurgical control. Orders flooded Bethlehem Steel before Taylor and White left Paris. The chemistry was solved. But scaling laboratory batches measured in pounds to industrial production measured in tons would reveal why European metallurgists remained skeptical of American metallurgical ambition. Laboratory success proved meaningless when Bethlehem Steel attempted commercial production in August 1900. Taylor and White's experimental furnace handled 50-pound batches with precise manual temperature control. Industrial furnaces processed 5-ton batches using coal fires that varied 200 degrees across the massive crucibles. The first production run, batch number 47, overheated to 2600 degrees. Tungsten carbides formed throughout the steel, creating brittle particles that shattered tools instantly under cutting loads. $1,800 in materials and labor lost in a single failed batch. Batch 52 underheated to 1800 degrees, producing steel that looked perfect but lost hardness immediately when heated by cutting operations. Batch 61 heated unevenly, the outer portions reaching proper temperature while the center remained too cool. Half the tools worked beautifully. The other half failed within minutes. Metallurgists could not distinguish good tools from bad until machinists tested them under actual cutting conditions, by which time failed tools had already damaged expensive workpieces. 5 American steel companies launched desperate attempts to replicate Taylor and White's formula through industrial espionage. Crucible Steel Company of Pittsburgh hired 3 former Bethlehem workers who knew the alloy composition, but not the heat treatment precision that made it functional. Their tools failed 60% of the time, creating market confusion as customers could not determine whether high-speed steel was revolutionary breakthrough or expensive fraud. European manufacturers countered with competing alloys that promised similar performance through traditional metallurgical approaches. British manufacturers introduced super mouchette, claiming cutting speeds of 30 feet per minute through improved tungsten content. Actual shop floor performance rarely exceeded 15 feet per minute, barely better than original mouchette steel. German producers marketed Schnellstahl, with high tungsten content but wrong chromium ratios, producing tools that either cracked during heat treatment or softened under cutting heat. Swedish metallurgists developed Rapide using their nation's legendary iron ore purity, but the resulting steel proved too brittle for interrupted cuts where tools repeatedly engaged and disengaged from rotating workpieces. Samuel Morrison, the Bethlehem foreman who had struggled with tool failures 2 years earlier, now faced an impossible choice. American high-speed steel averaged 28 feet per minute cutting speed when properly manufactured, but 60% of batches failed quality standards. British Mouchet steel delivered reliable 12 feet per minute performance with consistent quality. Management demanded a decision. Should Bethlehem bet on unreliable American innovation or dependable European technology that guaranteed inferior but predictable results? Monsell White attacked the production problem with the same systematic approach that had solved the alloy chemistry. The fundamental issue was temperature control at industrial scale. Furnace operators judged heat by visual observation, calling out cherry red or orange heat based on subjective color perception that varied between individuals and lighting conditions. White developed pyrometric temperature measurement using thermocouple probes inserted directly into the molten steel bath. The system cost $340 per furnace installation, a significant investment that management initially resisted. The results justified every dollar spent. Temperature variance dropped from plus or minus 200 degrees to plus or minus 15 degrees. Batch-to-batch consistency reached 97%. Success rates climbed from 40% to 92% as operators learned to trust instrument readings over visual judgment. White added controlled atmosphere furnaces that prevented oxidation during heating and precise quenching bath. Temperature control maintained at 150 degrees plus or minus 5 degrees. Each refinement improved consistency and reduced the waste that made high-speed steel economically questionable despite superior performance. Bethlehem Steel patented the complete process in 1901 and began licensing American manufacturers at 50 cents royalty per pound produced. British Mouchet Company immediately filed patent interference claims, arguing Taylor and White had merely modified existing tungsten steel formulas. German manufacturers claimed prior art, presenting metallurgical papers that described similar alloys but omitted the critical heat treatment temperatures that made them functional. The legal battle consumed 5 years and $70,000 in attorney fees, while American manufacturers struggled with unlicensed imitation steels that damaged high-speed steel's market reputation. Dozens of companies produced alloys they called high-speed steel using similar compositions but inadequate heat treatment control. Machine shops could not distinguish certified Taylor-White steel from inferior knockoffs until tools failed during production runs. A single bad batch could shut down an entire factory for hours while machinists replaced damaged workpieces and recalibrated equipment. Customer complaints flooded Bethlehem Steel despite their product performing exactly as specified. The market confusion threatened to destroy high-speed steel's commercial viability before American manufacturers fully understood its potential. Taylor and White responded by trademarking high-speed steel as a certified designation with guaranteed composition and performance standards. Licensed manufacturers received stamps to mark genuine tools, and Bethlehem published detailed specifications that allowed customers to verify authenticity. But certification meant nothing if American machinists refused to trust tools that glowed red-hot during normal operation, violating every safety instinct that 3 generations of metalworkers had learned through painful experience. The next barrier was not metallurgical or commercial, but psychological, convincing workers that deliberately running cutting tools at temperatures that looked like imminent catastrophic failure was not just safe, but represented the future of American manufacturing. Ernst Hoffman, master machinist with 30 years' experience at Cleveland Manufacturing, refused to operate a lathe with a glowing cutting tool. Traditional practice was absolute. When a tool heated beyond hand-touch temperature, you stopped immediately before it failed catastrophically and sent shrapnel across the shop floor. Hoffman's father had lost 3 fingers to a shattered cutting tool in 1871. The idea of deliberately running tools at cherry-red heat violated every safety lesson Hoffman had learned through decades of careful work. Insurance companies threatened to void factory coverage for what adjusters called reckless operating practices. Machinists United, the national trade union, refused to endorse high-speed steel until independent safety testing proved the glowing tools would not explode under cutting loads. A tool failure at Cleveland Works in October 1903 injured 2 workers when an inferior knockoff high-speed steel shattered, driving metal fragments through a leather apron and into a machinist's thigh. Newspapers ran sensational headlines calling it death steel, ignoring that the failed tool was unlicensed imitation, not genuine Taylor White certified material. The machine tool problem created a second adoption barrier that threatened high-speed steel's commercial viability, even among manufacturers willing to accept the safety risks. Existing lathes and milling machines had been designed for cutting speeds of 10 to 15 feet per minute. High-speed steel cut at 40 feet per minute, and spindle bearings overheated at the increased rotational speeds. Feed mechanisms designed for slow cutting could not advance workpieces fast enough to utilize the new tool's capabilities. Machine frames vibrated destructively at high speeds, and belt-driven power transmission systems slipped under the increased loads that faster cutting generated. The economic tension was brutal. High-speed steel reduced tool costs by 60%, but upgrading machine tools to handle the new cutting speeds cost $4,000 to $12,000 per machine. Factory owners who had just invested in modern equipment faced the prospect of scrapping perfectly functional machines to exploit tool steel improvements. Machine tool manufacturers initially resisted redesigning their entire product lines, insisting that tools should adapt to machines rather than forcing expensive equipment obsolescence. Cincinnati Milling Machine Company broke ranks in 1904, investing $180,000 in complete product line redesigns, featuring heavier cast frames, gear-driven spindles replacing belt drives, and forced lubrication systems that prevented bearing failures at high speeds. The gamble required selling enough new machines to recover development costs before competitors copied their innovations, betting that high-speed steel would transform the industry rather than remaining a specialized curiosity for technically advanced manufacturers. In 1925, a museum curator from the Smithsonian Institution contacted Bethlehem Steel, requesting samples of original Taylor White cutting tools manufactured in 1900 for historical preservation. The factory foreman denied the request with a single-sentence response. Still using them. Tools manufactured 25 years earlier remained in active service, cutting hardened steel components with the same precision they had demonstrated at the Paris exhibition. European tool steels from the same era had long since become metallurgical footnotes. Robert Mouchet's tungsten steel was obsolete by 1910. German Schnellstahl disappeared from catalogs by 1918. Swedish Rapide ceased production in 1922, unable to compete with the American alloy that European metallurgists had dismissed as crude empiricism lacking theoretical foundation. The longevity revealed something fundamental about the difference between European and American approaches to metallurgical innovation. European metallurgy emerged from centuries of university tradition where theoretical understanding preceded practical application. Researchers needed to explain why an alloy worked before recommending its use. Taylor possessed no university degree in metallurgy, having studied at night while apprenticing in machine shops. White was a chemist, not a metallurgist, bringing fresh perspectives unburdened by conventional wisdom about what combinations steel chemistry permitted. Their competitive advantage was willingness to test combinations that textbooks insisted were impossible, trusting experimental results over theoretical predictions. The heat treatment breakthrough illustrated this philosophical divide perfectly. European metallurgists avoided temperatures above 1,600 degrees. believing higher heat burned steel and destroyed its crystalline structure. Taylor and White recognized that what appeared as damage actually created beneficial metallurgical transformations. Modern materials science discovered in the 1930s that extreme heat dissolved tungsten carbides into the steel matrix. Then precipitation hardening during tempering created dispersion, strengthening that explained high-speed steel's remarkable properties. Taylor and White never understood the mechanism. They simply trusted their cutting tests and documented what worked regardless of whether metallurgical theory could explain the results. The economic transformation validated their empirical approach with brutal clarity. Manufacturing 100 steel parts in 1898 required 47 hours of labor and $28 in Mouchet steel cutting tools. The same parts in 1925 required 12 hours of labor and $8.40 in high-speed steel tools, a 75% time reduction and 70% tool cost reduction. Those improvements enabled mass production at price points that created middle-class consumer markets for products that had been luxury items a generation earlier. Automobiles transitioned from custom-built vehicles for wealthy customers to standardized transportation. Household appliances shifted from handcrafted rarities to factory-produced necessities. Hardware components moved from blacksmith forges to precision machining operations. Frederick Taylor died in 1915, Monsell White in 1912, neither living to witness the full industrial transformation their metallurgical breakthrough enabled. Their patents expired in 1918, releasing the technology into public domain where 47 American steel companies began producing high-speed steel without royalty payments. The democratization accelerated adoption as standardized specifications replaced proprietary formulas. The American Society for Testing Materials established designation systems still used today, with Taylor and White's original 18% tungsten, 4% chromium composition designated as M1 grade, unmodified after 125 years of continuous production and use in machine shops worldwide, proving that systematic empiricism could create solutions that outlasted the theoretical sophistication European metallurgy had defended for centuries.